In this video, we would like to see one question being solved from the GATE 2012. Why we have chosen this particular question? Reason is that we find very less explanation, very less details about this particular topic, which is general plane motion of rigid bodies. And one more important thing to take this question into account is that we have many solved papers in the market, we have many notes in which GATE questions are being solved, but for this particular question we have lots of answers given by lots of solved papers. Some has given 0, someone has given D, and we have many other options too. And many people find it difficult to solve or get the concepts right, because as you all know, GATE doesn't repeat the questions, but they tend to repeat the concepts in a far more higher complicated way. And after seeing this, we'd like to take this question into account, and we'd like to solve this using all the ways possible, so that even if there is any kind of complicated questions in this particular topic, after seeing this video, you'll be able to answer it as simple as that. It's going to be very easy for you once you know the method in which we get the particular answer for this question. Fine. We'll dive into the question now. Like they have said, a solid disk of radius r rolls without slipping. Like this is rolling without slipping, which we also call it as a pure rolling concept. Rolls without slipping on a horizontal floor with an angular velocity omega and angular acceleration alpha. The magnitude of the acceleration of the point of contact on disk is. This is the main important thing which we need to know. Point of contact on the disk. This is most significant point in this particular concept, because many people might have know this before, but I would like to say this again. The velocity at the point of contact is 0, and we have given one animated video too, animated GIF. If you could just go through this particular video, we'll come back again. Just watch this. Gears are rotating, and the rolling thing are also rotating. But we don't call it as a rotating thing, but we call it as a rolling thing. While the gears are rotating, it doesn't have a linear motion, right? But while the disc is rotating on the floor, it has a linear motion too. Like this question can be drawn like this. Let's say I'm having a disc on the floor. Have a gap, so I'm just drawing it again. So as I've said, I'm just poor at drawing, so bear with me please. So I have a omega, I have a alpha, I have a velocity v0 and a acceleration at the center. Let's say this as 1, let's say this as b. Let it be any variable, doesn't matter at all. They have asked the acceleration at this particular point. Now many people might be aware, and we are going to derive it too, velocity at the point b, which is 0. That's what we have been explained in this concept. Gears are rotating, but it is not moving in a linear direction, whereas this particular disk is rotating and it's going to have a linear movement too. Okay, it is moved from this position to this position. This is the distance it has moved after rolling. But does the gear move linear in a linear displacement? No, not at all. But this pure rolling goes, because of the fact this disc is in contact with the particular stationary ground. This particular point is going to be 0, and we are going to have lots of velocity profile, and we have given you a PDF document which you can download it from the description, and we have given you a profile, velocity profile for this particular thing, which goes like this. If this is the center point of contact, velocity is maximum at the top, and it goes down up to 0 point over here. In the mid we have a velocity, VO is going to be R omega always, and at the top we are going to have, let's say this is going to be A. VA is equal to 2R omega always. Okay, so this is one of the thing. For our question, no need to have these concepts, but this is very good for you. If you could just know this, you could solve any kind of question in this particular topic. Fine. And having been said that, we'll go into a general derivation of rigid body. Okay, let's say we have a rigid body, and I have a point A and I have a point B, and there is a distance, absolute distance let's say this is RA and let's say this is RB and the distance is RA by B. Okay, sorry, RB by A. Let's coming from B to A. All these are vector quantities. I am going to have, let's say if you want to reach B through A, how will you go? Very simple. Go to A, then go from A to B. So radius of B is going to be RB is going to RA plus R of B by A. Going to very simple. How do I reach B through A? Go to A then and go from A to B. So this is going to be very simple. I am going to differentiate it with respect to time. So what is the distance by time taken? This is actually a vector quantity, so its displacement. So I like to denote it by a vector quantity. So respect to time, we get displacement by time taken is obviously is going to velocity VB equal to VA plus VB by A. So this is the first step. We are going to know this particular concept first. Okay. This is the kinematics of a general plane motion of a rigid body. Now we'll apply this particular concept over here in this pure rolling. What am I going to do is I'm going to have a solid disc rolling on the floor. This is point O. This is, let's say this is point B. Okay, any variable, doesn't matter at all. What am I going to do right now is just apply this particular equation over here. So for me, VB is going to be VO plus VB by O. So are you with me? Fine. So this is VB plus VB by O. This is nothing but velocity of B as seen from O. For example, let's say this is the marker. Okay, this is stationary, and for you this particular marker is moving from. For you it will be from right to left, I guess. Okay, for you it will be from right to left, right? What am I going to do is, I am going to move this side and it's going to move this side. I am going to move this side, it's going to move. Okay, this is the relative velocity. That's what is going to happen over here. And this is going to be a different value. The value which you see is different. The value which I see is different for this marker. That's what we have it as a relative velocity. And once we have this, we'll know that VB by O is going to be omega into RB by O. Okay, this is the normal thing which we get. We all know V equal to R omega R, it depends, and VB by O is going to be omega into RB by O. Now I'm going to get the velocity for this particular point B. Okay, now let's go. I'm going to rub this. Now before going ahead, I'm going to denote it with the unit vector quantities. Everything is a vector quantity, so it's mandatory for us to have a unit vector quantities for all the things involved in this. Now the thing which I'm going to have is, this is going to be I, positive J and positive K. Into the paper is negative, out from the paper is positive for the K. Now this is going to be the same. Now I am going to take this. VB is going to be, first is going to be V0, it's moving, right? So V0, what direction, what unit vector quantity it is? I in the positive. This is positive I. Then VB by O is omega into plus omega. The rotations, this is clockwise rotation, always has a unit vector quantity into the paper. Okay, so which is like minus K unit vector. Okay, clockwise disk, if it rotates clockwise, if it has a rotation in a clockwise direction, our unit vector quantity is going to go into the paper. So into the paper for us, for our notation is going to be negative. So omega into minus K, negative unit vector into RB by O. From the question, if you could see, RB by O is going to be velocity of B from O, sorry, radius of B from O. What is that? What is this distance? This is going to be R from the question. This is going to be R, and it goes in the downward direction. J is in the upward, which is positive, and I'm going to have R into minus J unit vector. Okay, so let's make this clean so that you'll not get confused. So I'm going to have, let's say I'll draw it smaller, I, j and k. So I'm going to have r in the minus j unit vector direction. So it's going to be very, very simple. V naught into I cap. So we have two minuses, so it's going to be plus omega r. I'm going to multiply. So k into j unit vector is going to give us k into j is minus, right? So minus I unit vector. So we already know V is equal to omega r. So what am I going to do is VB equal to V naught into I cap plus V naught into minus I cap. So solving this, I'll get V naught I cap minus V naught I cap. Cancelling out, I'll get the velocity to be 0. So first it might be non-intuitive that velocity at this point is going to be 0. This is very simple, like if it's in contact with the stationary ground surface, obviously it has to be the velocity has to be 0. So that's what we have derived and we have got the answer through the vector quantity. Now we'll go into our acceleration analysis. See how easy it is once we know the concepts clean. Okay, we are going to derive the acceleration analysis and we are going to find out the answer. Before going into acceleration analysis, I would like to derive a very small thing, like which is going to be from this V equal to omega r, right? We are all aware of it. Even this can be derived, not required as of now. So I'm going to differentiate this with respect to time. So dv by dt is going to be d omega by dt, let's say d omega r, and r is constant, so we take it out. So dv by dt is going to velocity divided by time taken is going to be acceleration. So r is constant, we take it out. D omega by dt is going to be alpha. So alpha is going to be a by r. So keep this in mind before solving. Okay, now we'll dive into the acceleration analysis. So this is the key for us. This equation is going to serve for us so that we could start our analysis with. I am going to go ahead with like VB equal to V naught plus omega into r b by 0. So this is without the vector quantity. Now I am going to differentiate it, add a unit vector quantity, get the answer. As simple as that. Once you know the differentiation and the concept of unit vectors like k into j, I into k, you will be able to solve this as simple as that. I am not sure why there is very less notes on this. This is going to be really easy for you as of now. See, now as usual I am going to differentiate this particular velocity divide with respect to time. I am going to get AB equal to A naught plus, and this is going to be differentiation of d omega into rb by 0 divided by dt. Since we have two terms, I am going to use the chain rule differentiation. So differentiate this particular thing, leave out uv dash whole dash equal to u dash v plus uv dash. So this is going to be AB equal to A naught plus d omega by dt into rb by 0 plus next thing I am going to have is omega. I will have omega as it is, omega into omega is already there. I am going to have drb by 0 divided by O divided by dt. So this is the thing we got. Now I am going to solve this further. We are going to get the answer as easy as that. I am going to add a unit vector quantity now along with all those things. So acceleration of B is going to be like A naught AI to the power I cap, A naught in the I vector quantity plus d omega by dt is going to be, already we have got d omega by dt is going to be alpha. So alpha is also in the clockwise direction, so it's going to be a unit vector minus k, okay, d omega by dt into rb naught. Rb by 0 is already r in the minus j cap direction. We have seen it already, r is going to be in the minus j cap direction. Now after that we are going to have plus omega into k cap minus k cap. We have seen it already. Let's make it clean. So omega into minus k cap direction. So once that is done, again we are going to have dRb by R naught. So already we have differentiated dRb by R naught, which is VB by O on the first thing we have got. Once you differentiate, you get this as dRb by O by dt is going to be VB by O, right? So this can be expanded as omega into RB naught, RB of O. So omega into minus k cap into R of minus J. Okay, so almost you have got the answer. Now I am going to solve this further. AB equal to AO I cap plus alpha, we have found it out earlier, A by R. So minus A by R k cap into R into minus J cap. So this is going to be plus in between, plus omega into minus k cap into this is going to be omega R. So k into j is going to be this minus into minus gave into plus. So again we have sorry, k into j, which is going to be minus I. So solving this further, so this k into j, already we have two pluses, so 2 minus we are going to get plus AR into R. So k into j is going to be minus I cap. Okay, so this is done. Now we have omega R into minus I cap. So we have 2 omegas, omega square R. So already 1 minus is there. So already 2 minuses are there. So plus. So k into I is going to be positive j cap. Okay, now AB equal to A naught into I cap plus RR gets cancels, A of minus I cap, which is also minus A of I cap plus omega square R into J cap. So solving this, we get cancelling out omega square R in the J cap direction. So option D. So positive like this, omega square R in the J cap from the option B. So this is how we got the answer. It might look like a lengthier thing for you, but once you know the concept, you could be able to solve in, I could say, like 2 to 3 minutes. Even after knowing this, you will be able to solve acceleration on any point. Like let's say this is C, this is D, and let's say this is E. You would be able to solve on any point on the pure rolling concept. This is the fruit of knowing the exact concepts behind the question. Now we'll see one more way to solve this acceleration, which is more easy for this particular point. Okay, that's what is being given normally, I could guess. We'll see that too, because it's easy. I'm not going to miss it out. So titled is acceleration of linear displacement or linear translation. How it's gonna be in a pure rolling? So if it's like this, this is going to be this, 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 and this. Then acceleration of pure rotation. This is going to be like this. So this is going to be tangential acceleration, and we are going to have centripetal acceleration. So this is tangential, this is centripetal. I could use a different marker so that it's easy for you. This is centripetal acceleration. So now taking this point alone here and here, I'm going to solve it like this. I'm going to have this particular thing over here, this particular thing over here, and this particular thing over here. This is omega R, and this is also, alpha R minus alpha, and this is plus alpha R. This is going to be omega square R. You are going to cancel it out, and you are going to get the answer omega square R. This is also one of the way, but foolproof is this way. Once you know this, you will be able to solve any kind of even more complicated questions. If you could come across in the future GATE papers, you will be able to solve this. If you have more doubts, please do comment in the description. I will be able to answer it for you.